Hello everyone, we're still in chapter 12. We're still considering the rotation of a rigid body, and we consider the quantities that are involved in the rotating object. So what is a rigid body? It is of course an object whose size and shape don't change as it moves. So we're going to consider in this session a tug. So what is a tug? It is the tendency or ability of a force to rotate an object about a pivot point. So the pivot, sometimes we call it fulcrum. So in this session, you will learn that tug depends on both the force and where the force is applied. So a longer wrench provides a larger tug. What does tug do? Tug is to rotation, what force is to linear motion. Tug causes an object to have angular acceleration. Newton's second law for rotation is the angular acceleration is the tug over moment of inertia. Much of rotational dynamics will look familiar because it is analogous to linear dynamics. Why is rigid body motion important? The world is full of rotating objects, from windmills, tubings, wheels, and all those things. So a tug is a rotational effect caused by the turning force. It is denoted by that tug sign. It is a vector quantity. It is measured in Newton meter. It is positive when the force tends to produce a counterclockwise rotation, and it is negative when the force tends to produce clockwise rotation. So target is defined as the product of the force and the lever arm, where the force is perpendicular to the lever arm or lever arm is perpendicular to the force, which means we have a tug which is equal to perpendicular force times lever arm, or a tug which is equal to force times the perpendicular lever arm. So let's consider this example where we have a door and a hinge where the door is rotating, or which is the point about which the door rotates. Then we have a force there which is acting on this L. As you can see here, the force is acting perpendicular to the lever arm. Lever arm is the distance from the hinges to where the force is acting, that is L. So here, so we're going to have the tug which is equal to force times the lever arm. It's both the force and the lever arm are perpendicular to each other. Let's consider the second example. Again, we have a door here and a hinge about which the door rotates. Then we have the force now that is acting at an angle. So in this case, we have the tug which is equal to F times lever arm sine of theta. The other thing that you can do here, we can resolve the force and get the vertical component of the force and the horizontal. So the horizontal now, since it's going to pass, is horizontal, it passes through the pivot. It does not have an effect on the rotation. Just like if you push the door here, it doesn't rotate. It must have a vertical component. So we also have an example where the force is acting horizontal. So if it is horizontal, which means it passes through the pivot, then it does not have a turning effect, which means the tug is 0. Okay, when discussing tug, the line of action, of course, is the line at which the force acts. That is the correct answer is number B. A rigid body is in equilibrium if, of course, the net force is 0 and the net tug is 0. So when the net tug is 0, we say the sum of the tug clockwise is equal to the sum of the tug anti-clockwise, or the sum of the counterclockwise tug minus the sum of the clockwise tug is equal to 0. Then we know that the object is at equilibrium, and the rigid object is at equilibrium either when the object is stationary or moving or rotating at a constant speed. A rigid body is an extended object whose size and shape do not change. No? So with the object that is rotating the parabolic. Let's consider this example. The four forces shown have the same strength. Which force will be most effective in opening the door? Again, we have a hinge here at the end. As you can see, F4, these forces are equal. F4 has a small lever arm. So let's consider this one. F3 is acting at an angle. So which means the force that is going to have a turning effect here is the vertical component, which is going to be, of course, less than F3. So F1 has a longer lever arm, which is the distance from the hinge up to where F1 is acting. So F2 does not have any turning effect because it passes through the pivot. So which means the force here that have the most effective turning effect, of course, it is F1. The correct answer here is F1. Tug measures the effectiveness of the force at causing an object to rotate about the pivot. Tug is the rotational equivalent of a force. In a bicycle, your foot exerts a tug that rotates the crank. The effectiveness of a force at causing a rotation is called tug. Tug is the rotational equivalent of force. We say that a tug is exerted about the pivot point, as you can see here on this range. So the pivot is here, is the point in which the nut is rotating. Then the force that has the biggest effect is when the force is acting perpendicular to this surface of the range. So we can use now this angle phi, or we can use theta here. So this force has the biggest turning effect if it is acting perpendicular to the surface of this range. So what you can do now, if this force is not acting perpendicular, you can always look for that component that is acting perpendicular to the lever arm or the surface of this range. So mathematically, we define this symbol of tug as tau. It is a Greek symbol. So now if F is not acting perpendicular to the distance, like the lever arm R, which is denoted by R or L, then we determine the component of F, which is, of course, opposite to phi. Then it is, we use sine of phi there. Okay, as I've mentioned, tug is measured in Newton meter. In SI units, here. Then in English units, it is foot pounds. In American units, it is what? Pound feet. The ability of a tug to cause a rotation depends on the magnitude F of the force. Distance R from the point of application to the pivot, and the angle at which the force is applied. So tug, of course, has a sign, positive for counterclockwise rotation and negative for anticlockwise rotation. So if you get a tug that is negative, then you just interpret the sign. So it will be clockwise. Let's consider this example. Which type force on the wheel applied at point P will make the net tug 0? Okay, as you can see, you can take this one and put it here. It will move from here up to P. Then we can shift, of course, a vector from one point to another point, as long as we maintain its direction and magnitude. Then this can come in close. If the forces closes, then we say the object is at equilibrium. So which means the correct answer here is A. Let's consider example number 8. Lewis uses a 20 centimeter wrench to turn a nut. The wrench handle is tilted at 30 degrees above the horizontal, and Lewis pulls straight down on the end with a force of 100 newtons. We need to calculate the torque exerted by Lewis on the nut. So as you can see, this force is acting vertical downwards. So we need to get this component that is perpendicular to the surface of the wrench. So either we use this, we get the phi, which is 120 degrees, or we can get this angle. Since this force is perpendicular to the surface, so it's clear that this angle will be 30 degrees. So now this will be 100 cos of 30 degrees. Then you can be able to calculate. The force is 100, the lever arm is 20 centimeters, so convert it into meters. By dividing by 100, then you get 0.2 meters. Then the formula is this: tau is equal to F times the perpendicular lever arm, or tau is equal to the perpendicular force times the lever arm. Then we get the component there, which is cos 30. Then we make substitution. 100 times 0.2 cos 30 is 17.3 Newton meter. And the direction is clockwise. Yeah, let's see. If you hold the nut, if you hold here and you rotate, so it's clear this causes a clockwise rotation. Okay, the first tutorial problem, you need to do it by yourself at home. Lewis now uses 20 centimeter long wrench. The wrench handle is tilted 30 degrees above the horizontal. You need to calculate the torque exerted by Lewis on the wrench. If he pulls on the end with a force of 100 newtons, okay, the first scenario is perpendicular to the wrench. Then the second scenario is parallel to the wrench. So we need to calculate the torque. Okay. Net torque. The figure shows the forces acting on the crankset of a bicycle. F exerts a force on the axle to balance the other forces and keep F net equal to 0. The net torque about the axle is the sum of the torques due to the applied force. So you can see mathematically it is denoted by this. So the torque due to gravity is found by treating the object as if all its mass is concentrated at the center of mass. So then we have the torque here due to gravity. And if you hold here this point, and you'll see that this causes a clockwise rotation about this point. That's why the torque due to gravity is negative. A net torque causes an object to have angular acceleration. So we use this Newton's second law about the rotating object. So in the absence of a net torque, so we have a net torque which is equal to 0. Okay. So torque is measured in Newton meter. Moment of inertia is denoted by I, which is measured in kg meter squared. And angular acceleration is denoted by this sine, which is measured in radians per second. So this is alpha, sine alpha. So we can even make the net tag the subject of the formula. Then we get moment of inertia I times the angular acceleration. Let's consider this example. The engine in a small airplane is specified to have a tug of 60 Nm. This engine drives a 2.0 meter long, 40 kg propeller. Calculate the angular acceleration caused by the tug. So let's check what is given here. So we take this as a rod. So we're given, okay, the formula is tug equal to moment of inertia times the angular acceleration. Then we make what we are looking for, which is angular acceleration, the subject of the formula. Okay, so the tug is given, but the moment of inertia is not given. So we need to calculate the moment of inertia. So we take the propeller as the rod, then the formula is 1/12 ml, where m represent the mass, l represent the distance. So we make substitution, then we get the moment of inertia, then we substitute it into the formula with the tug, then we get the answer, which is measured in radians per second squared. Okay, starting an airplane engine, we've assumed a constant angular acceleration, which is reasonable for the first few seconds, while the propeller is still turning slowly. Eventually, air resistance and friction will cause opposite tugs, and the angular acceleration will decrease. At full speed, the negative tug due to air resistance and friction cancels the tug of the engine, then the net tug will be 0, and the propeller turns at a constant angular velocity with no angular acceleration. Okay. Tutorial problem number 1, you need to do it by yourself at home. Two equal forces F1 and F2 with a magnitude of 60 newtons are exerted to rotate about the center of a disk with a diameter of 20 centimeters. So you can see we have two forces that are equal. So we have F1 and with F2, then we have a diameter. They're acting in the opposite direction, but they're acting equal along the same direction, horizontal. So now you need to calculate the moment of inertia. Then you need to calculate the tug caused by the forces. Then you calculate the angular acceleration caused by the tug. Okay, static equilibrium. A rigid body is in static equilibrium if there is no net force and there is no net tug. An important branch of engineering called statics analyzes the buildings, dams, bridges, and other structures in total static equilibrium. Then, yeah, those who are doing civil engineering and mechanical engineering, you know, they learn more about, about this static equilibrium. So for a rigid body in total equilibrium, there is no net tug at any point. Okay, let's consider this model here. So we have these two forces that are acting up, then this one, the downwards force balances these two forces. So the object is not rotating and it's not moving. Then we say the net force is 0 and the net tug is 0. Tutorial problem number 2, which is actually number 3. You need to do it by yourself at home. A 3-meter long ladder with a mass of 32 kilograms leans against a frictionless wall at an angle of 60 degrees. We need to calculate the reaction forces N1, N2. We also need for 10.2 to calculate the tug at the wall due to gravity. So at the wall, you need to calculate the tug here due to this force. Of course, we have lever arm from the center to where the reaction forces acting, or from this point where you were looking for the tug up to where the force is acting. Okay. Balance and stability. Stability depends on the position of the center of mass. Number A, as you can see, base of support. The tug due to gravity will bring the car back down as long as the center of mass is above the base of support. This makes sense. Number B, the vehicle is at the critical angle where its center of mass is exactly over the pivot. Okay. Which object is in static equilibrium here? The object will be in static equilibrium if the forces, horizontal forces, balance the opposite forces. As you can see, these ones at A, they are equal, so they don't balance. The forces acting towards east are twice that one acting towards west. So it's clear that D is the correct answer. So the forces Q is the balance, the one Q west. What does the scale rate? Okay, let's check. So we have a load here with a force of 1000. Of course, here we have a pin. So the reaction force here, of course, will be equal to 1000 as well, downwards. So which means the scale is going to read 2000. Solving rotational dynamics problems, because we use Newton's second law. So tau, alpha angular acceleration is equal to the net torque over moment of inertia. So as you can see here, this object is not moving. It is stationary. Then the net force is 0 and the net torque is 0. Tutorial problem number 3 or 4, a 50 kg load is placed at 2,0 meters from the end of a 1000 kg beam. The beam is kept stationary by the cable and the wall as shown below. The length of the beam is 6,0 meters. As you can see, here is the load with 50 kg. Then there is a cable here that balances this beam, and this side is the wall. So the questions, you need to calculate the tension in the cable, tension in this cable, and also you need to calculate the force exerted by the wall on the beam. So the beam is in a static equilibrium. Okay, that is the end of the tutorial session. Thanks for taking part. All the best.